Before we really get into chapter 3, I want to look at chapter 2 a little bit. There's two kind of preface videos that you're going to see in this module. One exits chapter 2, and one talks about why we're transitioning to the information we want for chapter 3. I'm going to go over to the full screen here. This gets weird if you haven't for 2 seconds, but I'll get the browser up. There we go. Now, chapter 2 in the front of your textbook in the key formulas can really be broken down to formulas. And a key thing that we're going to have to start understanding is formulas are a way of talking about things. They're a shortcut for saying what the things are. But they're not the things, and they're not how to compute the things. They're usually a quick little instruction, and mathematics is a language. And so when we say class width is the range of the data divided by the number of classes, this is an instruction on how you create the class width. Sometimes in very short notation, like the relative frequency is here, and sometimes in much more longer words. And what we want to do is we want to be able to distinguish and use the concepts of the things. Then we want to use the formula to help us figure out how we're going to construct it. But in the end, then we compute it. And these are kind of three separate ideas. So I'm going to switch over here, and I'm just going to kind of look at these three separate ideas. So we have mathematics as a language. And the things it describes are patterns. And those patterns are concepts. And we're starting to learn concepts on how we describe data. We spent a lot of time talking about where the middle of data was with mean, median, and mode. And then we talked about how the data varied with variance and standard deviations. And we were able to talk about z-scores. And so those are the concepts of those things. The mathematical language tells you how to construct those. And so what we'll have is the concept, the formula or language of it, but none of that then is the actual computation. And these three things can live separate of each other. I've watched a lot of people, they'll especially prevalent in high schools about a decade ago, was they'd learn statistics on their TI-84 and they would plug everything into the data set, go to this screen, and you get your standard deviation, but very little time on concept. And they were also weak on formulas. I also know other people that I teach that they'll be like, just tell me the formula, I know how to compute it. So if they could pick the formula out, they would know how to compute it. But because they were saying, tell me the formula, they're missing the concepts to choose the formula. And this is something we have to be very aware of right now, is that we're living in these three worlds, or these three ideas at once. This is what society wants from you. This is what you want from mathematics. We want the concepts. We want the language and the computation to predict the future. Right? Mathematics was invented to predict the future. Right? Primitive peoples had problems that they needed to count or measure. And once they counted and measured, that solved problems for them. And so that predictive nature of it is the concept. And this is the part that falls into that everyone hates, which is the word problems. Now, the formula language is the thing that we spend a lot of time memorizing or reconstructing, right? And I'll use the mean is the sum of each piece of data divided by the number. And this is a sample mean, right? And so this language tells me things. This is the symbol we're going to be using for the sample, mean. This tells me to add up each piece of data divided by the number of items in the data. But the concept of the mean is it's a measure of a middle. And it's a good estimator of what a collection of what value we should use to assign to a collection of things. Now when we go to compute this, let's say I have a set of three things. Well, I'll use test scores. We like doing averages with test scores. So yeah, I got a 40 on that test. Right? I'm not rocking it. But I tried really hard, and I was able to get an 82 on my last test. And so if these were a straight average, I could find the mean, the middle of this data. And we do that. We use our averages as a way of representing how we did in a course, because we say that's a good estimate of the overall abilities. But the actual way of computing it is I take 40, 70, and 82, and I add them. And so, 11, 19, and now I have to divide by 3. All right, so I summed all my pieces of data. Now I'm dividing by 3, which goes in. I got a 64. And that is the things that we're dealing with here, coming across. So I'm going to go through the equations in Chapter 2 and focus on concept, from formula to concept. For computation, I'm relying that we're going to be using the Excel examples or calculator. Right? I'm focusing on Excel as my means of calculation in my examples until you guys tell me you're doing it in a different way. So, where's my, sorry, switch mice here. Ooh, infinity. I really love this. Sorry about that. And back over to here. And so, class width was a way of making frequency diagrams. In fact, when we first went to making histograms or graphing these things, we would represent things in classes. And so we would collect our data in bins. And so the idea of class width and midpoints were ways of determining where data would be within a clustering that we would make. So I'm going to come back over here. I want to find a way to do this with. I'll find a way not to get infinity in everything I do. And so class width was we take the range of the data. So we take the largest piece of data and we'd subtract the smallest piece of data. And that would give us the range. And the class width, which I'm just going to abbreviate as CW, was the range divided by the number of classes we wanted, or the number of bins. And then you always round up, so as you went through, your data would fit in. And what this ended up doing, I'm going to just draw 5 classes here, is it made pockets on the number line that we could put our data into. And we would look at the value, and if it fell within there, we'd tick off blocks. And we again use this as a way of making histograms. And so this is a kind of organizational format of looking at how we're going to arrange data. And then when we talked about these individual classes, we would talk about their lower bound and their upper bound. And the midpoint would be the upper bound plus the lower bound divided by 2. Right? And so constructing and building these is something that you will practice, and it's worthwhile practicing them. But the formulas we're seeing here relate to that. And those are the concepts that come. So when you're looking at your formula sheet, these relate to those concepts. All right, let's continue down this formula sheet as we work our way through things here. And population mean and sample mean. Now, and weighted means. I'll do all 3 means together, or all 4 means. We'll do all of these here. For a population, we're using Greek letters to say that we have everything that we're looking at. And so we'll use the Greek mu for the mean, and then we'll use the sum of all the data pieces divided by the total number of things. And we use a capital N when we're talking about the population. The sample mean is the sum of all the data divided by the number of samples we took. And a lowercase n talks about samples. Weighted means say that each piece of data has an additional value, some weight to it. And so we sum the data times its weight and divide by the total weight. And the mean of a frequency distribution is we sum the midpoints of the data times their frequency. And it relates back to the relative frequency. When we build these histograms, or when we build our frequency distributions, we count how many pieces of data fall into a bin. Well, we can turn that to a percentage. This right here, the relative frequency, which is the class frequency divided by the sample size, is going to be one of our best tools because we can turn what we observed into a percentage. And as we talk about probability, we'll see how percentages can predict future events. And so this kind of simple looking f over n is going to come back and haunt us. And this mean of a frequency distribution is going to come back and haunt us. All right, then in variance, and variance and standard deviations are related. In fact, the standard deviation is the square root of the variance. I will speak in standard deviations more often than not. Again, we use Greek when we're talking about the population, and we use the Roman alphabet when talking about samples. And so the population variance, or the standard deviation, is sigma for S, and it's sigma for standard deviation. What this does is the upper part, x minus mu, says how far away the piece of data is from the mean. We then square that so that we get a positive value always. And we add up those positive values and we divide it by the number of things in the sample. And so we're getting an average distance away from the mean. This works out as kind of being an average distance for the data. And that talks about, well, on average, each piece of data is this far away from the mean. That's the concept of what variance does. And that's the concept of what sample variance does. It's about, on average, how far away is each piece, is my distribution. And so it takes the average distance of each piece of data away. Now what we're going to find as we go into more detail is that normal distribution, that bell curve, things fall into particular regions. And if you know where your data is, you know how much percent of stuff came before it. And the empirical rule is a way of stating that in standard deviations. And that comes from our z-scores, which is kind of the last thing that it mentions down here. The z is the x minus the mu divided by standard deviation. And it's a way of measuring the distance a piece of data is from the mean relative to the spread. So it takes into account the spread. And those are the concepts that you don't have to have mastered yet. But they're going to keep popping up as we review this. So coming out of chapter 2, those are the very important things that come back. In fact, sum up anything that you want to kind of hold in your notes, chapter 2. Relative frequency, what that means. An idea of what a mean is, a way of representing the middle of the data. An understanding that variance tells you the average distance all your data is from the mean, or how far it spreads. And that the z-score talks about how far away you are from the data within the particular spread you have. These concepts will come back up over and over again. All right, that's my chapter 2 recap.